So, hi guys, this is Dr. Edwards. So, this first video adds on to what we've already been discussing in our class in 303. We started out with vectors, uh, simple vector addition, vector multiplication, the dot product, the cross product. Now we've done some vector differentiation. We did some vector operators, the gradient, the curl, the divergence, and the Laplacian. I've given you homework with these as well. I don't think I've given you homework totally yet with the operators, but I will rectify that soon. What I want to talk about today, though, is vector integration. Just as you can do regular scalar integration of the basic function f of x back in your calculus class, now we can talk about vector integrations, whereas the author has it written here. Suppose that capital R is a function of some R1 along the ith direction, some function R2 along the jth direction, and so function R3 along the k, where I, j, and k are constants. These are constant unit vectors. Always when you see I, j, and k, they are considered as being constant. Then when you now look at, and firstly we're going to talk about indefinite integrals, which leads you to another function. A definite integral leads you to a number because you're going to evaluate the function after you integrate it from the lower limit to the upper limit. But an indefinite integral always leads to something of this form, some function plus some constant that's there to be evaluated as the problem need to be. So therefore then, if you have this function, you can then talk about the formal integration of some vector r of u. Du is the integrating variable, and you're going to get some function, a vector function, s of u plus the constant of integration. And then if you do a definite integral, as I say here, now you integrate the function itself at the upper limit and at the lower limit, and that's what you would have, which is a number. So in one case, the indefinite integral is a function, and the indefinite integral is a function, like so, and the definite integral is a number with units depending on what it is for the particular problem. Okay, that's the most elementary case. Now, here's an interesting thing now. So when we get to these kinds of problems, you will see that we begin to talk about what's called a line integral. L-I-N-E-I-N-T-E-G-R-A-L-S. What is a line integral? Okay, so let's see then. So what you're going to find, suppose you have this regular position vector. It is a vector drawn from the origin out to some point xyz in the xyz plane. That's what R is. And dr then is going to be the differential of R. It is then dxi, dyj, dzk is d vector R. So what we like to talk about, though, is this operation. We do some operation beneath the integral sign before we integrate it. And in this case, when you do the dot product, you dot dr with a, and you get then the sum of three scalar integrals. That's what the dot product effectively gives you. And there's a special case of a line integral that is called a circular integral. And so what we put this little circle in the integral representation in the distorted S, and that means you're going to integrate around a closed path. It doesn't have to be a circle. but it's a closed path in some way. That is the formal definition of a line integral. Now we have several definitions to put out there, so I'm going to go through those firstly, then we'll come back and do some homework, do some problems, and then we have some homework problems. So that's the dot product. And let's see here. So, okay. All right. So there are various theorems that we have. Obviously, then, if you're going to integrate some A dot dr from P1 to P2 is independent of the path from P1 to P2. If A is what's called a conservative function, if it is not a conservative function, this neither 1 nor 2 is true. Only in a conservative vector field or conservative function is 1 true and also 2 is true. All right. I want to make sure that you have that. Now, so here comes another situation. So here we want to talk about integrating in a spatial arrangement, an area integration. So here, a surface integral. You're going to integrate over, say, this top circle or the bottom surface, or you may integrate over the whole surface, top, bottom, and sides. That's referred to as a surface integral. All right. And the form of notation is this structure here. And then you can have, then, special case surface integrals of a scalar over that surface. Surface integral of that scalar over a vector surface. And then you can have the operation with the differential underneath the integral sign. But keep in mind, though, you can't do anything with these operations under the integral until you get it into its standard form. You can't integrate it until you get it into a standard form, like back in your elementary calculus class. All right. After surface integrals, now there's volume integral. So you integrate over a three-dimensional a spatial object, spatial region, and that becomes a volume integral, as it's called. So now the author here, let me just go through one or two of these illustrated problems in my Sholmes outline for you to practice, and then I'll give you some homework, and I'll leave you for today. In this first problem that we have here, so the function is given. R is given as some function of u here, the x component, or the ith component, the jth component, and the kth component. So find then this indefinite integral a, and then in b find this particular definite integral. All right, so here we go. There it is. There you can see. You practice, you put the entire integral underneath the integral sign. And the integral of a sum is the sum of the integrals. That's what that represents right there. And now he does the power law integration. The integral of u du is u squared over 2. The integral u squared is u cubed over 2 plus the constant of integration. All that's in front of I. In a similar operation he does now. What is the integration of 2u cubed? It is u to the 4th over 4, but 2 over 4 is 2 plus the constant of integration, all multiplied by j. And then he does the same here, a similar operation. The integral of -3 is 3u plus the constant integration, all that times k. Then he simplifies. What does he do? He pulls the constants out to the right, so he's going to group them all. Because all this is a constant, he calls it C. Because ij, he calls it vector C. Because C1 times I plus C2 times j, C3 times k just becomes another vector that we call C. And so there we have it. Then we have this indefinite integral here of A. All right. Now he says, let's find this definite integral. And he does it in two different methods here. The first method is right there. Okay, so he just integrate the first expression, and then he's going to evaluate it from 1 to 2. So everywhere that it has u, he puts in 2 initially, minus the situation for 1, and then combine terms, and you get the final expression. He says you can also do it this way, which is fine. I really like this way better. There's no point in bringing in this constant if you're going to do a definite integral. Just leave that out and you solve it that way. Okay, so that's what I wanted to share with you. Firstly, this operation here. You can have many different formal operations underneath the integral sign. Like, no, the integral of A cross the second derivative of A with A cross the second derivative of A dt second. Well, before you can evaluate, you have to evaluate or simplify the integrand. Once you simplify the integrand, then, which is the quantity underneath the integral, then you can proceed to formally perform some integration. Let's see, do I want to say anything else here on this? There are now, next time, I'll give you some many different equivalencies, theorems. There will be the Stokes theorem, the Galison theorem. I'll bring in all of those, and those become some nice operations as well. Let me see, do I have the theorems here? If not, I'll let you go. I can also mention this once again. The curl is here, and we talk about how to find the curl. We've already talked about it. Okay, I think I'll quit for now. All right, I'll give you some additional homework. You keep working on the homework that you already have, and I'll give you some more. I don't know when I'm going to put it online, maybe later today or first thing in the morning. Have a good day.